Wait. Is it better?
Oh, yes, yes. Right, so how nice to see you again in person. Nobody's died in the past week, I hope.
What is wrong?
No, yes, get rid of that for the time being, sir.
Okay.
Right. One or two of you have been emailing me and saying that the training algorithm is tricky or difficult or you don't understand. Is that a general view? Right. At the end of this lecture, I don't think anybody's in this room. I will remain behind for as long as it takes. We will have a drop-in session. So over to you, and I will go over anything so far. At the beginning of term until now, if you've got any problems, get them sorted out now. Don't leave them until the end of the next term, because there's a nasty little event called an exam coming on then. Right. On Monday, we developed a training algorithm for an analog neural network. Now, I don't want to go over that again, but the basic principle was you started off with a weight vector W, you tested it against a input pattern which you know which class it is, it's class positive or negative, or your face versus your face, there's a real problem there. You have assigned the two categories of inputs to positive and negative. Those are the labels the system gives. And in training, you test the original weight vector, which in the very first case is random. I started off with all zeros, for example, on Monday. It will then change, obviously, on the first pattern, but assuming the weight vector is non-zero, you will get an answer S. And that calculation of XS is a scalar product. And you can do it in two ways. W dot I. It equals the summation I equals 1 to D of Wi times II. And in two dimensions, it also equals mod W mod I cos theta. Now, theta is the angle of the. Now, this form of the scalar product, linear product, helps you explain what's happening in two-dimensional space. You can see how you're classifying the clusters. But this summation of product, a pair of pairs of I and W, works for any dimension. For two dimensions, it will be W1 times I1 plus W2 times I2. In 100 dimensions, it will be W1 times I1 plus W2 times I2 plus W3 times I3 plus W4 times I4 plus W99 times I99 plus W100. So that will work for any dimensions. So in practice, this is the thing you are using to calculate, train or test the neuron. This, however, will explain some of the problems that are occurring in two dimensions. We can look at those problems and see what the limitations of this method are. So having got the basics there, testing on the first pattern, if we have not an error, if there's no error, i.e. I've trained on your face and you are the positive class, you go in and it gives a positive score, that's no error. Trained on your face, you're the negative class, your face goes in, it's negative, no error. The weight is satisfactory for that first input pattern. If, however, there is an error, in other words, we're getting a positive response and it's a negative class going in, or a negative response and it's a positive class going in, we've got to change the weight. And the way we change the weight is to reduce the error. So if it's negative, and it should be positive, we want to make it more positive. A plus is going to be involved. If it's positive, and it should be negative, a minus is going to be involved. And the update to the weight vector is W prime. The updated weight vector equals the original weight vector W plus Ci. This is known, this is the input pattern, and this is the correction factor. And we want to detect the correction factor, and the correction factor is such that if this is wrong, W prime dot I, which is the updated scalar product, equals minus S, which will change the sign. Because if this was giving a positive response, and we want it to be negative, it will be minus S. If we were wanting a negative response, S is negative, what this will give us is minus S, it will be plus S. So you're adding. And we went through an algorithm which gave a correction factor C equals minus 2S over the input pattern, the scalar with itself. And that was a correction factor to update this equation here, which is fine if you've got a computer. But in exams, you won't have computers, and just get pretty messy and funny, nasty arithmetic, which any computer scientist can do if they write a program, so nothing is extra about that. So I then introduced an approximate method, which applies to this equation. And instead of using this correction factor, I simplified it to C equals plus or minus 1. Right. So when do we use plus 1? When do you use minus 1? If you've got an error, and this is positive, and it should be negative, you've got to make the new weight vector more negative. C would be minus 1. If it's negative originally, it should be positive. You've got to add something to it. C becomes plus 1. And that will give it just a bang-bang training algorithm, which should converge to a solution if a solution exists. And that approximate method has been used before.
So basically, every time we have to correct the weights, we use 1 plus 1 and minus 1.
Yes, if there's no error, do nothing. Keep the same weight. If there's an error, look at what the error is. If S is minus and it should be positive, add to the weight vector. If it's positive, error, it should be negative, subtract from the weight vector. It's still this, but C will be minus 1. So it's plus minus 1. I don't have to explain that to you, do I? No, got no mechanical engineers here. Right. Okay. So that was where we were at the end of the last lecture. And at the moment, don't give up, guys. Conceptually, the next 2 or 3 weeks is possibly the hardest part of the course. It will be new material, new ideas which you haven't seen before. When we come on to a digital model of a neuron, if you are awake in level 1, you should recognize some of the ideas behind it. And when we come to image processing, which will be next term, we are looking at similar operations to these scalar products. But in the case of image processing, we know what we're doing, at least we should do, so we don't have to find the weight vectors. It's just a matter of using them. So life will get easier. But the next 2 or 3 weeks, I appreciate it is new stuff for you, but it is simple. Well, everything is simple when you understand, isn't it? So get on top of it, and you'll laugh at the simplicity of it. Okay. Right. Some new material. And I want to concentrate on problems, because a lot of people think AI is so wonderful and it's going to work, but there are a lot of problems associated with AI. And that is mainly due to our lack of understanding. And again, computer scientists don't understand anything. They just use programs. Any computer scientists here? If somebody's leaving, she must be a computer scientist. Thank you. to my two-dimensional model to show what's going on. We never use 2 dimensions in real life, but it's good to be able to try and see what is happening. Let's take my two-dimensional space. This is dimension 1. This is dimension 2. I have a cluster of patterns, which I'll call class A. And they're all there. There's a cluster that's called A. And I have another set of patterns. Again, using these 2 guys. This guy's cluster in 2 dimensions. And I don't know what 2 dimensions would describe you. Pretty low resolution. I suppose height and weight is a possibility. But then that doesn't necessarily define you uniquely, does it? So it's only as good as the data. No, there's a class. And here's another class. Let's call this class B. And again, 100, 1,000, maybe a million examples, all vectors, all points in two-dimensional space. Now, the model we have at the moment, let's draw the model out. This is I going in. This is I1. This is I2. That's a vector. They go through weights. W1, W2. They go into a summer. And there is a threshold. Right. Now, if I apply that model as it stands, then it's going to create a decision surface. The weight vector is going to be focused or anchored at the origin of that pattern space. If we imagine a weight vector going out there like that, the decision surface will be a straight line at right angles to it. Let's go through there. If I have this is a positive class and this is a negative class, and if A is positive and B is negative, all those are going to be wrong, and all those are going to be wrong. And as I move the weight vector W, I can move it about. Clearly, the decision surface is going to move up there, and down there, and we are never going to get a position where the A's are on one side of the red line and the B's are on the other side. So at the moment, that model can't solve this problem. So do a drawback. The solution, bias. What is bias? Most books don't tell you. It's quite simple. It is another input to the summer. And that input during training has a weight associated with it. And let's call that W3. And the input to that weight is not dependent on the pattern. It is a constant. Let's call it K, usually 1. So computing, that can be hardwired to the value 1. So we've still got our two-dimensional data going in on I1 and I2, the input vectors. But we are now increasing the dimensionality. This machine actually is looking at 3D, 3 dimensions, 2 of which are pattern dependent, and the other is an augmented dimension. Now, the pattern dimensions, whatever the pattern data, will be I1, I2, 1. 1 is common for every test, every training pattern. But during training, this weight vector can adapt. So we're actually operating, although it's a 2-dimensional problem, we're operating in 3-dimensional space. Now I'll try and draw it for you, but my drawing abilities are not the best, but see if we can get the idea.
So it starts at 1.
Stuck at 1, yes, that's in a box. So if I put the green box there, there's the output S there. There is your box, that is inside the box, and S comes out there. So we've still got our S coming out, and we've still got our pattern data going in.
That's okay, constant K.
Constant K, usually 1, but it's got to be the same for everything. It could be 100, it could be 0.1, 1 is obvious. Don't go for 0, that's the one you shouldn't have. 0's a funny number. Right. Let's see if I can draw this now. Let's have my two-dimensional space. Now we'll draw, no, let's come down a little bit, I think. See if you can get your head around this. Draw it as a box. And this is dimension 1. This is dimension 2. This is the pattern origin. Which is I equals 0, 0. But for the weight vector, we have a third dimension, which will now make this square into a box. And I'll try and draw it fairly accurately, as accurate as I can. And so here I've got Does that look like a box? Oh, not bad. This is dimension 3, and this will be your value k. And the origin of the weight vector, W1, W2, and W1, W2, and W3, will be this variable 1, this dimension 2, this dimension 3, and that is not restricted to k. K is the input, but this will take a real value, so that will be an analog value. And the origin for the weight vector is that point there, and that will be weight vector origin. And that will be W equals 0, 0, 0. Okay. So the weight vector is now going to operate not in two-dimensional space, but in three-dimensional space. So instead of doing this, it can do this. Three-dimensional movement. So the weight vector, and remember this square is the area for positive coordinates of dimension 1, dimension 2, dimension 3. If I want to draw the complete picture, which would confuse you completely, there would be 8 of these boxes for each dimension being positive and negative. This is all 3 positive, so this will be plus, 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 and there's plus, plus, minus, plus, minus, plus, minus, plus, plus, there's 8 of them, counting in binary. So the weight vector is going to be centered on this point here, and it's going to be wandering around in three-dimensional space. That weight vector is going to define a decision surface, which will be at right angles to it. There's my weight vector going out. There's the decision surface. And that weight vector will be an area that moves through three-dimensional space. And at some point, it will cut this front surface. And the decision surface, in this case the area, will go through the origin of the weight vector, but it's not confined to the origin of the pattern vector. So if I have my pattern superimposed upon that class up there, if I've got, let's go to that, might confuse things. If I've got my class A there, draw the patterns, and I've got my class B down here somewhere. Which are all the patterns there. To separate those, I need a decision surface. So there's millions of them. The decision surface that will do the job is, oh, I haven't used before, a decision surface that goes through there. That would correspond to an area starting here, Going across there, and again coming down there, where it's coming from this point, it's going behind cluster B, it's emerging on the front face of the box on that line, and it's then coming out here, this, and it will go above A. So if it was in 3 dimensions, it would be a slice that cuts through the cube that intersects the front face with a straight line. Which means I can draw a decision surface to separate these two. And it also has a minor but quite, I suppose, interesting bonus. In this model, how do I classify the pattern at the origin? I can't. It will always be on the decision surface. Now, if you're using a pattern recognition system, of all the patterns that you will try, the obvious one is to put nothing in and see what happens. It's an easy pattern. All the other 10 to the 80 patterns are tricky. Maybe all black or white would be all test. You wouldn't be able to classify a pattern there because it would always be on the decision surface. But here, if the decision surface is coming from behind and coming out here, and this is that going to be B or A? It could be B. You can classify it. You can also classify patterns at the origin. So that's the mechanism of the bias. And as a matter of routine with all these problems, whether it's 2 dimensions, or whether it's 100 or 1,000 or 64 million dimensions, always add another dimension at the beginning. And that will enable you to have a decision surface. So now when we draw in 2 dimensions, let's go back to this model, with bias, there was my original problem. There is class B. There is class A, which is there. Before, I could only draw a decision surface there. Now it is quite legitimate if there is bias. A possible decision surface that will solve those would be that decision surface there. We could label that as plus, we could label that as minus, or the other way around. So that gives you much more freedom with the decision surface. Okay, does that make sense? Get a box of Kellogg cornflakes tomorrow morning at breakfast and put your pattern data on the front surface, have an origin at the back corner, have a pencil that's wandering around the room with a sheet of paper attached to it, see how it intersects the front surface, and you'll convince yourself that that decision surface is coming from the origin, it's coming in here, it's going under this surface, so there it is, and it's coming above that surface. So this is in front of the surface, that's behind it. That's bloody horrible, that doesn't make sense. Use your imagination, do a Leonardo da Vinci on it for me. Okay, so that's one problem, and that's a reasonably easy solution. Use bias. It enables the decision surface in 2D, decision surface can be in any orientation, not confined to origin. And that's the pattern origin, of course. Right. So that's the solution there. The next problem, number of training patterns. How many? As many as possible. As many as possible. You've seen the training algorithm. The more training patterns you have, the longer it will take to train. So increasing the number of training patterns has a training time problem. So, yes, it's indeed that's. I haven't had a drink at lunchtime. I can't think right. I think I better next week. It's been recorded. No, I didn't drink at lunchtime. I never do. Right. Let's take a difficult but solvable problem. 2 dimensions again. And supposing I've got a cluster call that A, and I've got another cluster, let's call that B. Remember, these are points, 2-dimensional vectors. That is perfectly solvable. There's no overlap of patterns A and B. They are distinct sets, but they are irregular sets. And if I try to put a decision surface through those, a linear surface, a straight line, clearly I'm not going to find, even if the straight line is not confined to the origin, there is no straight line that has all the A's on one side and all the B's on the other. So, that's a problem called linear inseparability. But before we start solving linear inseparability, let's look at what happens if we're just trying this out for the first time and we use a few training patterns just to see if it's going to work. So instead of taking those complete sets, comprehensive training set, let's supposing I take one A pattern there and one B pattern there. Now it's like me, I think I gave this example, I'll use it again, recognizing your gender or sex or whatever the work word is for whatever you are. And we're measuring that by the row you're sitting in and the seat number. Row 1, 2, 3, 4, 5, 6, 7, seat 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stupid thing to do, but I could do it. And here's a perfect one category example here. And her coding would be 2, 2. And there's another fine example up there. He's going to be 9, or he, she, I don't know what to use these days, I'm completely confused, but that guy there is going to be 9, 9, 9. Now, in the equivalent of this, it would be taking 2 patterns. And all I would have for training would be those 2 patterns. And if I had those 2 patterns, I could find a decision surface that would separate them. There it is. Plus, minus, whatever the 2 vectors are. And if, of course, I use that on this particular class here, that's my reference pattern for class 1. There's my reference pattern for class 2. Here is the surface that goes through that separates my 2 reference patterns. Okay, I think it's classified you right, my friend, by chance. But the 2 guys next to you, I think they will be classified as slightly wrong. And the same for you guys there. Yes, we have errors. Because the training doesn't represent the problem. So you've got to have large numbers of training patterns. Now, mistakes have been made in the past with this. People haven't realized it. They've tried something. And if we go to 6-dimensional patterns, lottery ticket numbers, 6 numbers, vectors in 6-dimensional space, I train a network to recognize the last 3 jackpot winning tickets, which I've got the numbers for, and the last 3 tickets I bought, which I now throw away because I train those as winning, non-winning tickets. That would converge to a solution, because those 6 patterns don't represent the totality of the global number system that we've got. And hopefully it's random. Hopefully there isn't a pattern there. But we could come up with a solution separating what were past winning tickets from past losing tickets. And I say 6 patterns. I chose 6 patterns carefully because the dimensionality of the vectors are 6 numbers, 6 elements. And there is a rule, which this rule typifies. If I have a training set size, the number of training patterns is equal to or less than the dimensionality. And in fact, this will be less because there will be a bias on this, of course, because I'm not going through the origin. If the number of training patterns is less than the dimensionality, it will always converge to a solution. And don't think that is a solution to the problem, because the totality of the set has not been represented. Yes, it would work on one pattern if that was the set there, and this was the set there. Yes, it would work. On those 2 same training patterns, the sets I gave to start off with were something like this. Oh no, came down there, whatever, another segment, it doesn't matter what it was, a very non-minute, distinct, it wouldn't solve that problem. And I've seen books and papers a long time ago published mass spectra recognizing chemical analysis. They took vectors which were 256 elements long, smashing up molecules and counting the intensity of fragments. And they were separating different types of chemicals from mixtures and whatever. 200 training patterns, 100 class 1, 100 class 2, and dimensionality 256. It worked. It fooled half the world at the time because it wasn't solving the problem, but it changed it from the training set. So, make sure you have enough training patterns. And as a rule of thumb, people have suggested the number of training patterns T has got to be greater than 3D, the number of dimensions. That's a rule of thumb. Some people have said this should be 10D. Now, it immediately creates a problem if you want to recognize pictures. Because if you're going to put pictures into a neural network, the easiest way to put pictures into a vector form is pixels. And, okay, for low resolution, 16 by 16, it's going to be 256 dimensions, 256 pixels. If you go into half beast, 1,000 by 1,000, it's going to be 1,000,000 dimensions. If you go to high resolution, it's going to be 4,000 by 4,000, 16 million dimensions. To guarantee that the system will train, you need greater than that number of training patterns. So, beware of that one. Right. We are going to be confronted by this non-linear separability problem, so let's have a look at a possible solution without going to high dimensionality. Yeah.
So basically, increasing the number of dimensions does not guarantee that we go to a solution. A solution, yes, but not the solution.
Less than the dimensionality, every partition will work. Just 2 random sets will be separated. It's not proven anything. If it does work, it could be the case that there are 2 type clusters, and it will work. Or it could be a much more complex set of clusters, and it doesn't work. And you just don't know. Now, the more training patterns you use, go back to that stocky one there. If I have a set like this, in one case I'm using that pattern, Okay, if I'm starting using more patterns, one up there, 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 one there, and so on, distributed through that whole set, I would get a much better representation of the characteristics of the class. But of course, it becomes harder to train them, because remember that training algorithm is iterative. You go through the training set, you've got to go through it again. And each time the training set, the number of patterns in the training set gets bigger, more chances of it going wrong. Tricky stuff. Don't dwell upon it too much, just be aware of this.
So you said bigger. So you have to do sigma and that to decompose.
You have to code them. It comes into things like deep learning, which is a failure type approach, or feature expression.
What's the difference between pixel and 3D tensor?
Huh?
What's the difference between pixel and 3D tensor?
A pixel is an input to a vector.
Okay, and tensor?
Tensor, that's mathematics, that's probably, it's just taking a representation on a graph of patterns.
Okay.
So these two dimensions would be a representation of 2D patterns. So it could be a 2-pixel image. And that pattern would be white, which would be brought down there, and black would be, that would be there somewhere. Right. Right, let's take a pair of sets, linearly inseparable, but not too complicated. Let's take a set. There's one set A, and there is set B. Okay, linearly inseparable. Imagine, yes, we'll have a bias on it. I won't go 3D, it gets too complicated. Imagine it's in 2 dimensions. If I've got a vector out there, a weight vector, so far it will define in 2 dimensions a straight line. The decision surface I want to solve that problem. Can we join the party? That would be the desired decision surface based on those sets. Right! So far, a weight vector will define a straight line. I don't want a straight line. What have I got to do to get a curved line? Here's a clue. The equation of a straight line is y equals mx. Quadratic, yes, that's it. Higher order terms, non-linear terms. So, higher order machines. Pens are running out on me. Oh, stop these pens. And I'll start with the first machine above linear, which is, some people say quadratic, but in the literature somehow it's called a quadric machine. Second order terms. So we're not only going to weight the dimensions, we're going to weight the squares of dimensions and the combination of pairs of dimensions. And hopefully that has the potential to curve the surface. So what do we calculate? An exhaustive second order machine, including all terms. Right. The calculation is going to be in the summation I equals 1 to d of wi I, and those are the linear terms. Plus, and I'll change the counter, the summation. Come in, come in. I'll change the counter to J. Another series of weights over all dimensions. Wj, Ij. The square terms.
It's just I squared.
Yes. Dot. Plus, if it's going to be exhaustive, we need all pairs of terms. Double summation, if I can get this right. Ijk equals 1 to d minus 1. L equals k to d of w k w l I k I l, and that will be the pairs of terms. Now that looks complicated, and that makes mathematicians happy. What does it really mean? Let's give you an example of a second order machine.
Is it just the I squared? Yeah.
Yes, single term I squared, and pairs multiplied. Right? So take a vector example. I equals, I think I'll go for 4 dimensions. Yeah. I1, I2, I3, and I4. Right, what do we need to calculate? We're going to weight each of the inputs. So it's going to be, again, S the output. So I'll write it on the left-hand side this time. S is going to be W1I1 plus W2I2 plus W3I3 plus W4I4. Those are the linear terms. Standard, that's what you're used to so far. We also add weighted square terms. Instead of starting a different weight, I'll just carry on the weight index because it's going to end up with a big weight index, okay? So this is now going to be, let's write it in a different color, W5, and that is going to be I1 squared plus W6, I2 squared plus W7, I3 squared plus W8, I4 squared. Those are the weighting of the square terms. So those come from here. And I'll carry on with the weight increasing while we introduce K and L. And from then on, we're going to get a blue pen. plus W9, which is going to be I1, I2, plus W10, I1, I3, plus W10, 11, I1, I4, plus W12, I2, I3, plus W13, I2, I4, plus W14, I3, I4, is that it? I1, I2, I1, I3, I1, I4, I2, I3, I2, I4, I3, I4. So that's increased the dimensionality effectively to 14 dimensions from 4. One thing missing. Must have forget the bias. So it goes to 15 dimensions. Now, if we did that, we're making a real burden for ourselves because the dimensionality explodes. It's using exhaustive terms. And if we were to use this will give D terms. This will give B terms, so that's W dimensionality, 2D. But this one here is taking all pairs. It's going to be D minus 1 over 2. First choice, D. Second choice, D minus 1. The order doesn't matter, divided by 2. So I think the number of terms here is going to be D. Number of terms there is going to be D. I think the number of terms there is going to be D times D minus 1 over 2. And if I were to go to dimensionality 50, 50 plus 50 plus, oh, call that 50, call it 50 squared, 2,500 divided by 2, 1,250-ish. Looking big, that's the main point. And of course, that would have an implication on the training set size. So you rapidly come to the conclusion that we cannot use an exhaustive system. So a concept came along round about the 1980s, I suppose. This was a non-exhaustive second order machine. Or it didn't even have to be second order, a non-exhaustive higher order machine. And this was called the phi machine. And what it is, it's a nonlinear transform. So if we start off with our input vector I, so 4 of them, I1, I2, I3, and I4. Instead of going into weights, it goes into a nonlinear transform. Producing a transformed vector, and depending on the transform, you can choose the number of elements. And let's call those elements y1, y2, y3, and y4. Let's have 4 of them. And having got those transform vectors, they then go into a discriminator. So we have our weights and summing. So there's your weights coming in. There's your summation. There's your bias. Oh, noisy a lot, aren't they? There's the threshold. Should I invite them in to speak a bit of the AI? Right, so that's the model. Where did you get the transform from? Well, strangely enough, people who proposed this suggested trial and error. How do you spell trial? T-R-I-A-L? Doesn't look right. Not that I've ever been on trial. Right. Now, we're running short of time, but next lecture, I want to apply this non-linear transform to a problem, another problem that came up in about the 80s, which threatened to derail AI, and this is known as the XOR problem. So we're going to now apply this method to the XOR problem. And the XOR problem is a classical non-linear problem. It's not just the logical XOR gate. It can be an analog XOR problem. An XOR problem is typified by logical XOR. If I was to plot A and B on 2 dimensions, the inputs are my dimensions. You should, I hope you all remember from level 1, that point there would be f equals 0. That point there would be f equals 0. Shut up! And that point would be f equals 1. And that point would be f equals 1. And looking at that as a logical pattern, there's no way I could put a straight line in there that has the f equals 1 terms on one side and the f equals 0 on the other side. That's the logical XOR. What's the analog XOR? The analog XOR would be a cluster of patterns there, and a cluster of patterns there, a cluster of patterns there, and a cluster of patterns there. Where could that occur? Character recognition. These could be examples of the letter A capital. Those could be the examples of the letter A lowercase. In most cases, they have the same meaning. And this could be B, and this also could be lowercase. So we could have subclasses in many classes. And another example in manufacturing of an XOR type of problem, if you're trying to separate the average from the extremes. 16-bit words. I want to detect or recognize all the 16-bit words that have 10 or more bits set to 1. So that, if I try and represent that in 2D, that could be a cluster. And I want the ones that are mainly 1s, that could be a cluster there, and the ones that are mainly 0s, that could be a cluster there. And again, that has that sort of XOR problem. And again, a straight line won't separate those. So we're going to apply the quadratic machine to this. We're going to realize that the trial and error definition of the transform is totally unacceptable. And we're supposed to be dealing with learning systems. So we will then move to the stage where instead of expecting an idiot computer scientist to specify a random transform, why doesn't the system learn its own transform? And that leads us to the multi-layer, etc. So that's the next 2 weeks. Right, I'm going to hang around for as long as it takes. Anybody has any problems? Have a 5-minute break and then we'll sort that out for you. I'll keep the recording going so there might be something useful coming from the drop-in session.
Didn't do it yet. No. I'm not.
Right, think about questions you want me to explain further. All right. You emailed me, did you? Yeah. Okay. You know it all, do you? Good for you. Bye. See you. Right. You going or staying?
Thank you, sir.
Thank you. Right.
This is going to the business classifier.
They're all defining decision services.
Yeah.
Obviously, that does it in a different way. The distance classifier has less problems with linear separability. Remember, with the distance classifier, you have to do a distance measure for every packet. With the neural network, it's just one. Once you've got the weight vector, it's just one scale. Right. What should I talk about?
Neural network from Chicago.
Big one beside.
You guys are learning some topology.
Are you happy with the training algorithm? Would you like me to go through another example of that fixed income training algorithm? It's all right, is it?
Is that what you went through today?
Yes, I gave you the results, but I didn't go through the proof
Oh, okay.
or the example.
I came like 10 or 20 minutes late, so I might rewatch it.
Okay. The algorithm is called the error correcting algorithm. It's the one that has the C factor is minus 2s over I dot I, and that's used to update the weight vector. The updated weight vector is the original weight vector plus C subtraction of the pattern that's wrong. And it's a C factor that we have to find, and there's a C which was derived last week. The approximation is C equals plus or minus 1. Okay, let's go through an example of training. Could be an exam question, you never know. Right, let's make up a nonsense problem. It might not work, but method is good. Give us a number between 0 and 1 and 14. 12. Give us another one. 7. And another one. 3. And another one, 13. Now you see what I've done now, I've created 4-bit patterns from the numbers. Start scanning from the top to get the vector. It is going to be 1, 1, 1, 1, 0, 0. Now, yes, you said 12, but it's not 12 now, it's the vector 1, 1, 0, 0. Okay? This was 14. It's now vector 1, 1, 1, 0. Again, scanning, the origin is always regarded as the top left with pictures. 1, 1, 0, 0. X is 1, dot is 0. 1, 1, 1, 0. And the other one, this was 3. No, it wasn't. It was 3.
So this is what happens.
Yeah.
So that's what happens when scanning pictures.
Yeah. That would be 3, which would be 0, 0, 1, 1. And that was 13, which is 1, 1, 0, 1.
So you scan left and right.
Yeah, so that's scanning, that's got a vector from a picture. This was a real image, these would be huge. Okay. Right, I'm going to call this the positive class, and I'm going to call this the negative class. Now, in the class, I started off with a 0 vector, weight vector, 0, 0, 0, 0. Let's start initially, supposing you were born in your brain with this weight vector, if indeed this is a model for natural processing. Supposing you start off with 1, minus 1, minus 1. So that is my initial weight vector. Now, in training this, we have the pattern. That's a little red. Of course, this would be a computer program in the real world, but you're doing it by hand so you understand it. The pattern, you will have W dot I, the scalar product of the weight and current pattern. We have, try and have the same order as I gave last week, so don't get confused. Get out. Yeah, I called this the vector last week. This was the class. This was the scalar of the weight and the input. Correct. C for the update factor. And the updated weight vector. So those essentially are the things you have to calculate as you go through the training algorithm. And remember, this is my original weight vector there. So, the first training pattern comes in, which is 1, 1, 0, 0. And I've decided that is the positive class. No longer 12, vector 1, 1, 0. Positive class. Right, what is the scalar product of that with that? Work it out yourself. No, it can't be 0. Oh, it could be. Yes, it is. You're right. How dare I doubt you? Everybody see that? You got it? It is 1, 1, 0, 0. Dot 1, minus 1, minus 1, 0. And we're going to use the scalar product, the summation of Wi. So it is 1 times 1, which is 1, plus 1 times minus 1, which is minus 1, plus 0, plus 0. And as your friend said, the answer is 0. It is not correct. No. We want a positive response. We add positive class, C is plus 1. We add the current pattern to the current weight vector. So we're now going to add vectorially 1, minus 1, minus 1, 0, plus the current input pattern, which is 1, 1, 0, 0. And that is going to give us 2. Remember, it's an analog system. Even though we're using binary inputs, it's an analog method. It's going to give us 2 minus 1, minus 1, minus 1 times plus 1 is 0. Minus 1 plus 0 is minus 1. 0 plus 0 is 0. That is my updated weight vector, W prime. And so W prime now becomes 2, 0, minus 1, 0. Can't draw it in 4 dimensions. Right, we now take the next pattern, 1, 1, 1, 0. Yes? Right, input pattern. It's a positive class. I've defined it to be a positive class. It's giving a scalar product node. It's sitting on that decision surface, which is a 4-dimensional hyperspace. If you want to get technical, you can't imagine that. There it is. So, it's not correct. It's positive. Naught needs to be made more positive. Therefore, C is plus 1.
Okay, it's a condition. It's a condition.
So, you're adding, because we're using this update, where's it gone? The update we're using is W prime equals W plus CI. There's the original weight vector, that's what we want. We're adding C is plus 1, we're adding that pattern to that weight vector, which gives me that one. All with me? Right, next scalar. Yes, it's a positive class. There's the weight vector. There is the input pattern. What's its scalar? 2 times 1 is 1 times 2 is 2, plus 1 times 0 is 0, still 2. 1 times minus 1 is minus 1, takes it down to plus 1 and 0. I think it is plus 1. Do you agree?
Yeah.
It's correct, yes. No action needed. The weight vector is okay for it. Now we take the first pattern of the other class, which is 0, 0, 1, 1. It's a negative class. What is the scalar of this with the latest version of the weight vector? Minus 1. Is it correct? Yes. No change. Hey, we might be lucky here, it might work.
I thought you only think positive.
No. Negative pattern, it's negative pattern. That's why it's black. That was a planned session. I've been thinking about this for hours yesterday, how I'm going to present this. I'm doing it spontaneously. Right. 1, 1, 0, 1. It is a negative pattern. What is the scalar of that? That plus 2. No, it's not correct. We have to update the weight vector. It's giving a positive response. We want it to be negative, so C is minus 1. Yep. We therefore subtract the error pattern from the latest value of the weight vector, and that is going to give me a weight vector 2 minus 1 is going to be 1. 0 minus 1 is going to be minus 1. Minus 1 minus 0 is still minus 1, and 0 minus 1 is minus 1. And that's the weight vector you've got having passed through the training set of 4 patterns. But you've changed the weight vector here. There's no guarantee that the previous ones are still correct, because in changing that weight vector, you're moving the decisions. So we now have to go through a second iteration. And this is the big problem of this training algorithm. And I'll start again for the second iteration. It is going to be 1, 1, 0, 0, positive class. That's given the question. What is the scale of that with this one?
2, 0,
1 minus 1 is 0, 0. Okay, it's on the decision surface again, so it's not correct. So no. It's a positive class, we want to make it more positive. C has to be plus 1. We therefore add this pattern to the last weight vector. And it's going to be now 2, 0, minus 1, minus 1. Right, the next pattern, 1, 1, 1, 0. A positive class. What is the scalar with that?
1.
Plus 1. Is it correct? Yes. No action. You never know, it might converge. Let's take the next pattern, which is going to be 0, 0, 1, 1. It's a negative pattern. The scalar product of the base plus weight vector is minus 2. Yes. It's correct. Yes. No change. No change. Let's bring the lines down. And the final pattern.
1.
1.
1, 1, 0, 1.
1, 1, 1, 1, 1, 0, 1, thank you. It's a negative class pattern. The scalar is going to be 2 minus 1 is going to be minus 1. Plus 1, is it? Okay, 2. Yeah, plus 1. No. C is minus 1. Update the weight vector, subtract the current pattern from the weight vector, will give me 2 minus 1 is 1, 0 minus 1 is minus 1, minus 1 minus 0 is minus 1, and 1 minus 1 is 0. So we've had a change in the second iteration. Do you want me to do a third? Okay.
No, it shouldn't be minus 6. Start digit should it be minus 6.
We're subtracting
Minus 1.
that minus this. It's minus 1 minus 2, thank you. Now, if that was an exam, and you made that mistake, I'd be generous and I'd only take 1 mark off. If, however, we were getting a positive response from that one, and you updated the weight vector, you wouldn't know what you were doing, so you lose more marks on that. Okay. Right, third iteration. First pattern is 1, 1, 0, 0. Positive class. Its result is going to be 0. Is it correct? No. C is plus 1. I've now got to add there. It's going to be 2, 0, minus 1, minus 2. Next pattern comes in 1, 1, 1, 0. Positive class. The scalar there is going to be positive, yes?
1.
Plus 1, yes. No action. The next 0, 0, 1, 1, minus, yeah, it's going to be minus 3, yes. No action. And finally, 1, 1, 0, 1 is going to be 2.
It's going to be minus.
Minus 2 minus 2 is going to be 0. It's a minus, and you've got to update it. If that were an exam, in fact, if I ever set one of these exams, I would say do 3 iterations. Give me the weight vector at the end of the third iteration, even if it hasn't solved the problem. Because some of these problems can go on forever. Actually, there will be a solution to that because it's 4 dimensions and we've only got 4 training down. But when you start scaling these up to pictures, you've got no chance. And it's this business of the classification being a decision surface. Now, this cannot be biologically plausible, because when we're learning stuff, we don't have to have all these iterations which go on. Given the brain works at 10 meters a second, whereas electronics works at the speed of light, it will take us a millennium to learn anything if we have this method. So clearly, it's interesting from an engineering point of view, it's biologically inspired, it's not a neural model. Yep.
And the correlation between the wave factors is increasing by -1.
Yeah, there might be a pattern in it. Again, it's an approximation. So
You guess a lot from it.
you might probably, if I was using this one, which is the better one, it would converge quicker, it wouldn't have that pattern. You can get into a loop. And when they built that machine, which I showed you a picture of in the 50s, they had no idea that whether it would work or not. And it didn't work initially because they were trying to solve a non-linear problem. And they actually had to put a transfer, they had to use it, they were really the first people to use this time machine idea. It was a bodge. You put something on the front end to transform the image. They didn't really know what they did. It was quite a sensible idea. And that led to the fine machine and the non-linear transform. And that idea was taken up over the years. We learned from what they did. They couldn't simulate it in those days. No computers. Had to build about 384 motors whirring away to change the weight.
If we were to use the C equals to -2s, what would be the value of s? How would we implement that?
There's rest.
Oh,
That's the scale product, that was it. There's S. Okay, guys?
Did you go the S?
Chain code.
So that algorithm was called the training algorithm.
It's a training algorithm, yes. This is called the C, I've got it off now. This one is called the error correcting feedback method. This is called the fixed increment. Because the fixed increment C is either plus or -1. Or variable increment, fixed increment.
Can you say that again?
Variable increment, C depends upon the error and the current pattern. This C is just constant, minus plus 1. You're just hitting it. If it's wrong, you punch it and shove it in the other direction. Boom, boom, boom. Whereas the fixed increment is much more controlled. It's squeezing on, you start to respond, you don't squeeze so much. So that helps as an analogy. Right. Chain code. Take an image.
And let's see what it just fixed.
There we are, there's a shape. Can you see that? That's supposed to be all covered in. Right, and if you store that image, how many bits would it need? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 9, so 63 bits to store it. If you don't store it as an image, you can store it as a chain code. And the chain code will enable you to do some primitive matching with other patterns. The chain code is an operator. You note the 8 adjacent directions. And we label them. Mechanical engineers would label them 0 to 8, 1 to 8. You being more sensible people can save 25% of storage by labeling them from 0 to 7. Because 1 to 8 requires 4 bits, 0 to 7 just requires 3 bits. On this mark, 0, 1, 2, 3, 4, 5, 6, 7. And that operator, this is a pixel from one of these squares. And you imagine or you write a program such that this operator starts off here and it scans the image across and it keeps going until it finds a non-zero pixel. Again, this is assuming the images are black and white. And the first position it would end up on would be there. It's got its 4 directions 1, 2, 3, 4, 5, 6, 7, 8. And they're labeled 0 to 7. Right, you start scanning the directions from 0 and you look for the non-zero pixel. No, it's not there, it's not there, it's in direction 2. That's the first entry in your chain code. So pattern X is going to be a string of bits, numbers, 2. You then move to that direction. Now you could start scanning from 0. Sitting there would be 0, 1, 2. It would be 2 again. And that would be okay. But when we get down to this region here, underneath the image if you like, if you start scanning from 0 when it's sitting there, and remember you're not a human looking at this image, it's a program, it will look there and say, hey, that's not a background, that is the direction of the next thing. To avoid that, after the first position, instead of scanning from 0, you scan from the direction you moved in, the opposite direction plus 1, which is a sort of modular addition. We moved in direction 2. The opposite direction of 2 is 6, plus 1 is 7. And if we start scanning there, when the image is sitting there, it will start looking there. Now that will guarantee when you get round the corner and under the image, you will always start scanning from outside the image. And it will eventually end up, you won't get stuck. So we can do it almost by inspection. Let's get rid of that, it confuses things. So there, direction 2, start scanning from 7, so 0, 0, 0, 1, 2 again, 2 again, 2 again, so it'll be 2, 2, 2, 2. When we're sitting here, no, 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 yes, for that pixel it's 3. Move down to there. Start scanning from 3 plus 1, there'll be 0, it's going to be 5.
So after the 3, when do we start scanning?
We were there, we've moved into direction 3, we moved there, we start scanning from opposite of 3, which is 7 plus 1, it's normal. When we get here, however, we've moved in direction 5, when I'm sitting there, if I start scanning from 0, I'm in trouble. The direction I've moved in is 5. I start scanning from the opposite, plus 1, direction 2. So I start from this first scanning there, 2, 3, 4, 5. And it's 5 again. It's just to guarantee your outside image. The paper, I think the paper on that one talks of a blob skipping from the outside of the image each time it moves. That's a bit naff way of describing it. We call it modular addition plus 1, it's much more professional. That's all it is, keeping outside the image. So the final version of the chain code is going to be where we moved there, we've moved 4, 4, that will be 4, that will be 5, that will be 6, 6, 7, 7, 0, and 1. And that should be the training zone. And of course, you can, in theory, match these with other shapes, but remember, this is a coding of the edge, and the edges are noisy. And that's an idealized image. If I put an image under the camera, it's not going to fit the pixels exactly. So you're going to get noise on the edges. And in terms of storage, this might not, because it's such a small image, it might not save very much storage, but let's see what happens. Originally it was, what did I say, 63 bits. 1 to 63 bits. Now this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 directions at 3 bits, 45 bits. So there's a bit of saving on storage.
Yeah, I think you have an edge.
Have I? Even better, 40. 42 then.
No, I think you need to go 2, 2, 3, 3, 5, 4.
Yeah, I've taken it out. Mistakes are there for you to think. Remember that. You've got one over on me.
Why don't you write 63 bits?
Got it? The code, the only 8 directions. We're using 0 to 7, so we're only using 3 bits. So when you've got that as a set of computer words, you can divide it to 3, just like you do lots of changing, and you get the directions. So that one stuff was 3, wasn't it?
So have you done, do you remember the neuron modes? Neuron modes? Neuron
Models.
Yeah.
Yeah, this is the first one, and the model we're using is there is a representation of a real biological neuron. It has inputs. I1 down to IN, and that's your input vector I. It has an output, Z, S we call it. And the question is, it is extremely complicated in the real world. Very complicated voltages going in, wave patterns coming out here. We'd love to know what goes on inside there. So the simplest model, this model of 1950s McCulloch and Pitts, was that these are quantities coming in. We measure them as quantities. And they have significance. Some are more important than others, some are less important. Some can add to the output, some can subtract. And the model they used was to take the inputs I, and add a weight. A weight is simply a number. And if you want this to reduce the effect, it becomes negative. If you want to increase the effect, it becomes positive. And obviously you're multiplying, so that will increase the quantity. So you've now got weighted inputs. What's the easiest way to combine weighted inputs? Add them. So there is a summation and put a threshold on the output, and that is a potential model for that neuron. Now it's nothing like the real neuron, but it's interesting. Let's see how it behaves. And from that, we discover it's performing a scalar product. We can draw the scalar product in 2 dimensions, and we can see this decision surface coming. And we can now use it, in the first case, as a pattern or data classifier. The other role, which I'll deal with hopefully before Christmas, is using this model as a function approximator. Now, to use it as a function approximator, that's the standard model. We're simply putting a decision surface. Any pattern there is either in this class, that side, or that class there. That's classifying a pattern. But if you have patterns which are on the decision surface, and you deliberately want them to be on the decision surface, that is a way of actually modeling a function. So that obviously is going to be linear. So a single neuron isn't going to be very good at this. A host of neurons might be more interesting. You've got a jet aircraft flying. 1,000 parameters being monitored on that aircraft. It's a fighter, so human pilots can't react. There's going to be a set of conditions whereby that aircraft is stable. There's going to be another set of conditions where it's going to stall or crash or whatever. When the aircraft is flying safely, train a neural network which will follow the patterns of the aircraft being safe. So, having trained it, the decision surface, all the patterns are sitting on the decision surface.
So that's when it's safe.
That's when it's safe. That's when it's being trained. And it's going to be highly nonlinear. Then once if the system is going to work, once you are going to fly the aircraft, it's going to be one of these conditions. And the neural network will output 0 because the patterns are on the decision surface. If we get a pattern over here, the aircraft is going to stall. If we get a pattern down there, it's going to do something else. It's going to crash into the ground. And that was the aim of trying to monitor the system. You can do the same for a machine tool in a workshop. As the tools run, the vibrations increase. There's a set of patterns which suggests it's not working properly. And trained tool makers in the old days could listen to their machine and know it's running okay, or a simply car engine. Monitor your driving. If you want a burglar alarm on your car, you're driving a car quite normally. You're a very good driver, you're careful, you're very respectful. And so we train the neural network to learn that pattern of behavior. Then I come and steal your car, and straight away it's wheelies, and it's spinning, and it's trying to get on 2 wheels and whatever. Completely different set of conditions. We're not in the safe operating zone, and so it shuts down the engine. Doesn't work yet, and it has potential. But all these exciting things, people really have got to understand how these networks work. It's no good just picking up a neural network simulator and throwing data. And I suspect that's what an awful lot of people are doing. It's okay for non-critical applications like advertising. You bought a certain range of products at the shop and they've got a new product. Are you likely to buy it? Do they send you an advert or an email about it or whatever? Or dating your interests or voting habits or whatever, where the accuracy doesn't really matter. If you just get an improvement, that's what happens. But when you're on these safe critical ones, you can system go away. And this is a driverless car syndrome. Elon Musk has tested his system on 170,000 collision image sequences. At the pixel level, that's a drop in the ocean.
So when it tests a turning and it doesn't turn, it goes straight, is that because the decision is messed up?
It's seeing a set of patterns it's never seen before. And remember, when you're looking at the picture, you're doing a very high level assessment of the picture. All these systems can work on these numbers of pixel values. There's no consciousness yet in these things. And we haven't got any idea what consciousness is yet. Our natural systems have these electrical machines firing away. You picture a mum and dad and a good holiday, and a good party, and whatever. They come back to your head. How does that work? Even going from the eye to the brain, it's electrical signals. It's touching your face. Your face going into my brain is series of voltages. How would I perceive you?
So you said that the tester runs based on pixel, like scans like the image and then it makes a decision of the image, right?
It uses, but there's many, they throw at it as many sensors, and radar and LiDAR and things like that.
So for example, if in the future you were able to get like very, very accurate GPS location, could you like use that as?
It would help.
Okay.
But there's been some interesting, I saw some films once of when these systems don't work, recognizing animals and things like that. And you can work backwards. Certainly with the visual method I come on to say, you can easily frig the image by changing a few pixels, different values. Now, when we're looking at it, we smooth the image, we have a sort of global view. But by changing a few pixels, the perception of the image is perfectly fine. Yes, it's a lion, the neck, but bang, you recognize it.
But when you reverse Google search an image, it will still come back to the image even if you have drawn an image.
Yeah. Image retrieval, there's many ways of doing image retrieval. One is by colour content. So you get spectrum colour and then try and match that. The other is by shape recognition, which means the shape factor spectrum and how many shapes can you detect, what are their shape factors and whatever. And people are trying to recognise faces and images from sketch, which is pretty difficult. And humans can do it. And there's all the police photo fit images. They're not like the human being at the pixel level. Cartoons is another example. Nothing like the person at the pixel level, but we recognise them. And so getting that to work is even harder. But no, the colour match is interesting because it does work pretty good. Then you don't care when you do a search on an image. And I know you're looking for holiday snaps, and you get a picture of the pyramids in India, in Egypt, because it has the yellow and the gold and whatever. And another classic one, if you're looking at a country scene, which is green grass and blue sky, and then you show it, this is a take picture, and you show it a picture of a tiger at night, and that is yellow and black, and it will have the same colour mixture as the green and the blue of the sky and field. Perceptually, they are just ridiculously separate. Colour content. And the reason why you can't get the full colour spectrum of an image, you have to do the colour spectrum of the red, the green, and the blue, because that would be 8 bits, so that's 512 values, colour intensity. If you did it over the whole 24 bits, it would be spectra of 16 million entries. And you just can't match each other. That's all good stuff. Okay, guys, can I go now?
Yeah.
Any more questions?
Thanks so much.
How is it tough at the moment, or is it easy? And
In general or just this book?
no, me and Michael. Sorry, this is a very important one.
Yeah.
I would say this was really helpful for me because I couldn't attend the last two.
Yeah, okay. The pace is okay?
Yeah. Can we have like, cause I'm not sure this is a new course, but do you have like exam questions out there on Blackboard?
Well, we changed the exams last. We don't know how the exams are going to be this year. Last year it was just 4 questions, no choice. And we gave you a broad indication of the topics. Depends on what the questions are. In fact, if you're sensible, you look at the past pages. You don't really turn up. But again, you won't get the same questions from me ever again. You get the same method. All right.
This year.
Yep.
So that's what it was 1, 0, 1, 2.
Oh yeah. That's.
So it's 0, 1, which is just 1. And we opted for something 6, 7, 0, 1, 2, 3. Goes down there. It's 4, 1, just up there. Then goes back. Starting point. Then it comes to the middle.
I mean, those are so low resolution.
So how would you find the middle?
It doesn't have to find the middle, that's the only thing it ignores. Because if you're doing the edge, the only pixels you're looking at is that. Oh, yes, it might, oh, yes, it might start there, it might go down.
No, it goes to that.
Yeah, we did go down.
So we never find the
No. I mean, that never finds the middle. It's only operating on edges.
Does it not like assume the middle has a filled area?
Well, if it's a polar mint, it won't go to the middle. We'll just take that out. Now, if you wanted to detect a polar mint from a solid disk, shape vector. The area will be different, and the growth will be different as well. Okay?
Thank you very much, sir.
I'm not lecturing next week, I'll be taking on next week, I'll be 2 weeks time, online, just doing that.
Yeah, this would be the factor.
Yeah.
Then I switch to binary.
And again, you can recreate that from that, you can start the image, where's the operator come there? You take the operator, that's the first pixel, 1 in direction 3 would be the 1, so you can actually get the image from it. Okay?
Okay.
That's a full measure text as well. Right!
So, for heavy and learning, is that the same thing for?
Heavy and learning is a principle. It's a very simple principle. If you have a system, and it's not giving you the answer you want, make a change in one of the parameters. If that change makes the situation worse, go back to the original value. If it makes it slightly better, stick with the new value. And you train this with animals, you get the food out there, a couple of pedals over it, and if it's they can learn how to do the combination. Or a little kid trying to get a couple of resistor problem controls, trying to get the needle in the middle of the meter. You turn it, it goes further back into the, and that's the critical thing. And that's what we're doing there, we're knocking the system.
Using kids as studies.
Yeah. Right, let's stop recording this thing now. Gosh.
Could this be